Thank you everybody for joining this seminar. I'm Diego Turrini from the Italian National Institute for Astrophysics. I am a theoretical astrophysicist working on planet formation. My work mostly focuses on connecting the data that we get from the solar system and exoplanets and circumstellar disk to try to build a comprehensive view of planet formation across our galaxy. And this is the journey that I will take you into today. There is how these stars, protoplanetary disk, and the planets they form are all genetically linked, and how this connection shapes the characteristic of the planets and the habitability and their habitability. So the problem of the formation of planetary system and how it is connected to the formation of the star is a problem with a very strong pedigree, in the sense that this is a connection that has been recognized since the early 18th century with the solar nebula hypothesis by Kant and Laplace, and in the modern formulation of planet formation. The slides are not showing. Okay, so as we were saying, now with the support of graphics, the problem of the connection between star and planet formation is a problem with a pedigree, in the sense that it dates back to the 18th century with the nebula hypothesis from Kant and Laplace of the origin of the solar system from a disk-like structure surrounding the sun, and then more in modern planetary science with the early work of Safronos at the end of the 60s, so the beginning of the space era. However, for most of our history, the characteristic of planetary system which we could study this connection were only those of the solar system. And because of this, some of the information that we could derive are biased toward stars that are similar to the sun. And as we will see during this seminar, this is not necessarily the most general point of view. So it doesn't give us the full view of how planets form around other stars. And why this is important? Because when we look at exoplanets, we see that there is a huge range of diversity outside our solar system. Here you can see the orbital position and masses of the known planets. The diamonds are the planets of the solar system, and you see reported with the circles, the exoplanets discovered through different methods. And as you can see, if we were outside the solar system, we were to look at the solar system, the only planet that we would be able to detect would be Jupiter. So we would see the solar system as a one-planet system. All the other planets of the solar system are beyond or just at the the boundary of our detection capabilities. The planets that we see instead tend to be quite different. We see planets that are much more massive than the one in the solar system. You can see we have planets that are several times the mass of Jupiter, or thousands of times the mass of the Earth. And they tend to be also much more compact than the planets of the solar system. The orbit of Mercury in the solar system is around 0.3 astronomical unit. And so around here. And as you can see, more than 70% of the planets that we know today are more closer to the star than Mercury is to the sun. So our models need to be able to explain this, and they need to be explained to us if this is because there are different formation mechanism, or if there was some process that didn't act in the solar system and that transfer instead the planets close by. The differences between the planets of the solar system and the exoplanets are not limited only on how massive the planets are and where they are. Also, we have hints that also their composition are different. Also, we have it from the planets, for the planets for which we have the measure of the radius, and we can compute the density. And here you see highlighted by the lines the density of the Earth. So on the x-axis, we have the planetary mass. On the y-axis, the density. The crossing point between the lines of each color give you one of the planets of the solar system. So the Earth, Neptune in blue, and orange for Jupiter. And as you can see, the majority of planets of exoplanets that we know have a density between that of the Earth and that of Neptune. which is a range of densities that we generally don't have in the solar system for terrestrial planets, while at the for small planets, while for massive planets larger than more massive than 30 astronomical unit, so in the regime of super Neptunes, as they are called in the exoplanets community. We see, for example, that Jupiter represents a particularly dense case for its mass class, while the majority of planets that we know with mass similar to Jupiter tend to be much less dense. Again, is this a difference in the evolution, or is a different formation process, or a different formation environment that results in a different characteristics? To make things even more complicated, in the past 10 years, we've been able to observe the signatures of the possible signature of planets, specifically giant planets, in circumstellar disk and protoplanetary disk, so the formation environment where the planets are born. And one of the most striking features that we observed is that these gaps and rings that are thought to be the signature of the presence of planets embedded in the dust of this protoplanetary disk are at very large distances from the star. The small bar that you see in the bottom right of this panel is the scale of 10 AU, so that's the distance of Saturn from the Sun. And the majority of the structure are much more distant than Saturn. So we have systems that are much wider than the solar system and characterized by masses higher than those of the planets of the solar system, because these are the massive planets are the one we more easily detect. Again, is there something that is incomplete in our picture derived from the solar system or planet formation? Or do we have a different mechanism acting at different distances? Or yet again, we have that planetary system can be characterized by very different migration history. Before we venture into this journey, one thing that is better to get out of the way is the fact that none of the models that we have today is capable of fully capturing the diversity of planets that we know. So in the left plot, you can see the comparison of four population synthesis model. The one in red on the top right is the famous Baire model, which is mainly focused on accretion by planetesimal, which is the classical paradigm. On the right column, you have the models that instead assume pebble accretion, which is the more modern paradigm of planet formation. We will see more in detail in a few slides. And as you can see, overplotted, there are the density distribution of the exoplanets that you see also in the right. So we have the region of the hot Jupiters, the region of the cold Jupiter, and the region of the smaller planets on compact orbit. And these are the contour plot that you see here. The diamond are instead the planets of the solar system. And as you can see, some models are better in producing some characteristic, like for example, the Baire model is capable of reproducing the cold massive planets better than the other models, but has troubles reproducing the planets of the outer solar system. At the same time, the model of Drazkowski et al. 2023 with pebble accretion apparently is very good in reproducing the planets of the outer solar system, can fit both peaks of giant planets, the hot and the cold peak, but has problems in reproducing the terrestrial planets of the solar system. So at the moment, we don't have a complete theory of planet formation that can reproduce all the characteristics. And part of this problem, what I will try to show is that part of this problem is probably rooted in the fact that most models are still based more or less implicitly in assumption derived on our knowledge from the solar system. And so the template of the sun as the star from around which the planets form. So at the moment, because of this incapacity of our models of fully capturing this diversity, one of the questions that we are left to answer is what are the starting point and the building blocks of planets? Are they just the gas and dust that protoplanetary disk inherit from the native molecular cloud of the star? Are there the pebbles or the planetesimal, or a combination of both? At the same time, because of this predominance of planets very close to the star, where there is not enough mass to form, especially the more massive planets, there is the question, where do these do planets form? Do they form across the whole extension of the disk? Are there some regions that are favored? What are the processes that bring them where we see them? Do they migrate while forming within the disk, or the migration is a process that is detached from planet formation, as we generally consider it, and this is something more akin to later evolution? As you might have noticed from also the previous slide, most of the questions are related to the phase in which the disk is still present. And this is due to the fact that protoplanetary disks are the link, the genetic link between the star formation process, as they represent the tail of the formation process of the star, and the planet formation process that start within the circumstellar disk, the protoplanetary disk. So disks provide the environment in which planet formation act, and the planet formation is mostly shaped by the interplay between solid bodies and the surrounding disk environment. I was mentioning before that pebble accretion seemed to be the model that possibly captured the most of the characteristic of the exoplanets that we know today. Well, the family of planets that we know today. And it's also the class of model that is more recent with respect to planetesimal accretion that dates back to the beginning of modern planet formation. And the basic principle of pebble accretion are actually pretty simple. In the pebble accretion paradigm, it is assumed generally that you form a few planetary bodies within a disk of dust. And because they are embedded into this flux of dust that migrates across the disk, these bodies see a continuous flux of material that is reaching them, and they can accrete. Originally, at the beginning, they will accrete it like just due to the geometric cross-section, so it's going to be simply the dust they encounter. Later on, the gravity will become stronger and more effective in deflecting the orbit of the dust and increasing the capture efficiency. But the basic process is the fact that the bodies receive a flux of dust, a continuous flux of dust, and continuously grow. When it's goes beyond, brings the mass of the planets beyond roughly 1 Earth mass, the planets start interacting also with the gas, and the effect of these interactions is an exchange of angular momentum and the migration inward of the planet. During this migration, the planets continue to grow. At a certain point, it will reach a certain mass where it is capable of perturbing even more the disk gas and create pressure bumps. These pressure bumps basically act as dust trap, so the dust that reach the pressure bump is trapped and cannot reach the planet anymore, basically isolating the planet from his flux of feeding material, building blocks. And these are basically the fundamentals of pebble accretion. And something went wrong with this plot, which was supposed to show, let me see if I can show you, there it is. The fact that once the planet is isolated from the flux of pebbles, the only thing that can support its growth is basically the accretion of gas. So once the planet is isolated from the flux of pebbles, it starts accreting the gas. When the gas mass is equivalent more or less to the mass of the solid planet, the gas, the thermal pressure of the gas becomes incapable of supporting the gas and starts a process of runaway growth, where the mass of the planet grows much more quickly and the planet becomes much more effective in accreting the gas and opens a gap in the disk. We'll see more detail of this in a bit. So let's go back to the presentation. So to across these processes, there are two factors that basically controls the flux of material to the forming planet. One is the gas accretion rate, which is basically the flux of dust, of gas that crosses the disk toward the star, because the gas is losing angular momentum due to viscosity or other processes. And this flux of mass across the disk brings the gas to the planet when the planet is accreting gas, but also controls the global movement of material, including the dust. The dust, however, undergoes another effect. So there is a second component to their drift, which is due to the aerodynamic drag. Without entering the detail, basically the dust is moving with a different velocity with respect to the gas and is experiencing an headwind, which is basically slowing down. The process is the same as when you're flying and the captain of the flight announces that you have wind contrary. Your flight is going to last longer because the wind is slowing you down. And when you have a tailwind, these are pushing the airplane, increasing your velocity, and therefore allowing you to land earlier and arrive faster. This process depends on the size of the dust. And up to now, I was mentioning dust and pebbles interchangeably. And this is because basically they are the same in terms of physics. They are the same physical component of the disk. What changes and differentiates the pebbles from the dust is the size. So pebbles are the largest dust grain size, millimeter to centimeter, and are in the science range where they experience the maximum drag. So the velocity, the drift velocity across the gas is the fastest for the dust. These curves has been known since the 70s, so the first studies of the coupling of solids and the gas, and basically tells you how the velocity, the drift velocity of bodies changes depending on the size of the body. So for small bodies, you're on the left side of the curve. For small dust, the drift velocity is very small, and the drift velocity increases with the size of the dust until you reach the pebble range. Then you have the peak, which is the meter barrier, which you want to avoid, because during the meter barrier, the drift velocity of solids across the disk is too fast and basically doesn't allow planetary formation to take place. To give you an example, if you have a 1 meter size boulder and you put it on the orbit of the Earth at 1 astronomical unit, your boulder would fall on the sun in 50 years. So this time scale is too fast, too short to allow planet formation to occur. And then we have the right-hand side of this curve where we have the planetesimals, so the large planetary bodies, from the smallest asteroid to body the size of the moon. And in this side of the curve, the drag decreases the larger the body is, so it decreases with the size. So pebbles are basically in the optimal spot to have a lot of mass early on that can move fast and reach the planet continuously. While at the same time, your planetesimal will move limitedly, so they will see this flux of dust reaching them. This is the most physical that we will go in the seminar in terms of the art of physics. So don't get scared. Obviously, there is a problem, however. Aside from the very few cases in which we can observe planets embedded in protoplanetary disk, and we can study the protoplanetary disk directly, for the majority of exoplanets that we know, the disk has long been dispersed, and we only see the star and the exoplanets. Luck is on our side, however, because of the genetic link between stars and disks. So we can use the stars as a proxy to understand what was the formation environment in which the planets that we see around that specific star were born. So this link, the first thing that it tells you is that stars are as diverse as planets. So the stars are not always the same as the sun. On the left, you can see the distribution in mass of stars in different star-forming regions. And as you can see, there is a spread of at least, given that this is a logarithmic scale, at least an order of magnitude, if not more. Stars also differ, even if they have the same mass, in terms of the abundance of heavy elements, so the material that goes to form the dust. Because it is not easy to measure the quantity of all the elements in the stars, generally we use as proxy for all the abundance of heavy elements in the stars, the abundance of iron, because it's the element that is easier to detect, more reliable to detect. And also for iron, you can see that in this scale, the measure in a logarithmic scale, how much or less material there is, iron there is in a star with respect to the sun, we change by an order of magnitude. For minus 0.5 to 0.5 roughly, we have 1 decade. So even if we have stars with the same mass, if they have different metallicity, they will be characterized by the different abundance of heavy elements. And therefore, in principle, of dust and planetary building blocks. The study of disks and stars tells us that there is a correlation between the mass of the star and that of the disk that surrounded it. Specifically, this correlation seems to go with the stellar mass to the square. The power is not always a power of 2. It depends on the star forming region, roughly goes between 1.5 and 2. But there is a direct proportionality. So more massive stars, on average, have more massive disks. However, as you can see in this plot of the mass of the star versus the mass of the dust in observing the star-forming regions we were seen before, one of the star-forming regions we were seen before, there is a huge spread. So if we take a star of solar mass, so in this scale around 0, you see that the mass of dust in the disk can go from 10 to the 2 to 10 to the 0. So from 1 Earth mass to 100 Earth masses. So we have, with all the biases of the case, a dispersion of 2 orders of magnitude. Also, the gas accretion rate that crosses the disk toward the star is proportional to the stellar mass. Also, in this case, we have at least an order of magnitude of spread for stars with the same mass. So when we see a star around which where there is an exoplanet orbiting, we can use the mass of the star to get an idea of the average condition in which the planet was formed. But we need always to take into account that disks, like stars and planets, are diverse, and not two disks are the same. So there is a dispersion and there is an uncertainty in reconstructing this kind of the planet formation environment only from the knowledge of the star and the planet. And again, something is playing trick on us. So sorry for the continuous up and down. Why are we interested in this? Because pebble accretion tends to create a very direct link between the circumstellar disk and the formation process, because as we saw, the planet formation process, as I was telling you before, the pebble accretion process is governed by the flux of dust that reaches a planet that is available to supply mass to a forming planet. And the total mass that a planet can receive depends on the absolute quantity of material that is around the star, so the mass of the disk, if we assume that the metallicity is the same, and then on the metallicity, if we take a disk of the same star, the higher the metallicity, so the fraction of mass of the disk that is in heavy elements, the larger the flux of material. And this plot on the left shows you the cumulatively distribution functions of the mass of planets for disks of different masses. So starting from a disk that has a mass of 1% solar, you see that we can form planets that are up to the mass of Mars. Most of the planets will be in the mass range between 10 to the minus 2 and 10 to the minus 1, so the Moon and Mars. And we don't form any planet that is significantly more massive than the Earth. The dashed line is assuming that the metallicity is not solar, but twice as solar. So this increases the probability of forming planets as massive as the Earth or more massive, but we don't reach easily planets that are as massive as Saturn, so around 100 Earth masses. And we don't form planets as massive as Jupiter. If we increase the mass of the disk, going to darker and darker color, as you can see, the mass of the number of massive planets that we can form grows. So for disks that are 10% in mass, that of the star, they can represent 30% of the total population of planets. So the mass of the disk has the larger uncertainty because and variability, because as I was showing you, stars of a given mass can have disks that range up to 2 orders of magnitude in mass. And some of these disks can be also too little massive to form planets that we can detect. Then there is density. It can also allow planets to form more easily, but the effect is smaller than that of the disk mass. So you can see the shift due to the increasing by a factor of 2 the metallicity, it tends to be more limited. Let's go back to the presentation mode, and let's hope we don't get other surprises. The other factor that is important, I was telling you, is the gas accretion rate across the disk, because it controls the total movement of mass across the disk. The gas accretion rates across the disk introduces a temporal dimension into the problem. Why? Because it is known to decrease over time. So disks that are younger are generally characterized by stronger mass accretion rates, while instead the disks that are older are characterized by lower gas accretion rate on the star, meaning that there is a smaller and smaller flux of material crossing the disk as time progresses. And we can see the effect on planet formation in the plot here on the left. Specifically, you can see that the earlier the time, the lighter the color, and the most massive planets are formed only at the earliest time. And the more the time progresses, the fewer massive planets we have, until we don't get any, and we get, for the later time, we only get planet as massive as Uranus and Neptune top. So the characteristic of the disk introduce both the limit in terms of the mass of the planets we can form, and the limit on the time scale on which we can form planets. These are not just theoretical results, because we also have observational indication that is true. Specifically, here you see plotted the radii and masses of planets around FGK star, for which we characterize the mass homogeneously with high precision. And you see that the stars have been divided into 3 color beams. Stars with supersolar metallicity greater than 0.2 dex, or 25%, 50% solar, sorry. Between minus 0.2 and 0.2, this is a typo, and less than minus 0.2 dex solar, so 10 to the minus 0.2. And in this plot, the thing that we noticed is that the green points, so the planets orbiting stars that are subsolar in terms of metallicity, so they have less heavy elements. Even if you take the same disk and the same stellar and disk mass, they have in total less heavy elements. The masses of these planets tend to be the same as the most massive planets around stars with solar and supersolar metallicity. So the green points tend to sample the same region of parameter space as the most massive of the blue and the red ones. So the most massive planets are not particularly affected by the metallicity of the star. But the more metallic is the star, the more we see a population of low mass giant planets. So planets that are less massive than Jupiter, and they tend to reach masses of the order of that of twice Saturn, twice Neptune and that of Saturn, which is a population of planets that is absent for stars with subsolar metallicity. This is basically what we saw in the previous plots. If we form a planet early, we form planets in all disks equally. If we form a planet later, the number of planets decreases, and we see these planets only if metallicity can compensate the decrease in the mass flux. So if there is a higher metallicity, so higher density of solids, we can compensate the fact that there are less solids moving across the disk at later time, up to a certain point. If we have lower metallicity, we can only form the planets in the very early stages when we have a large mass flux. Interesting, this connection between circumstellar, the protoplanetary disks, and the pebble accretion is not limited to protoplanetary disk, but every circumstellar disk characterized by the presence of dust embedded in the gas, and therefore moving, experiences an aerodynamic drag and a drift, and characterized by an accretion rate, so in general, a movement of solid mass across the disk, can support pebble accretion. The most exotic case that I can present you is that of planets around double post-main sequence stars. So double white dwarfs are binary stars that undergo phases of common envelope, then they eject the common envelope, becoming white dwarfs. And when both stars have gone through this common envelope ejection of common envelope phase, they become a double white dwarf. During the ejection of the common envelope, it has been argued that part of the disk of the gas remain trapped around the star when it is ejected and form a circumstellar disk, which is not a protoplanetary disk because the star is not a pre-main sequence star but a post-main sequence star, but presents similar physical characteristics as the ones of protoplanetary disk. And in this study that was guided by Sebastiano Ledda 2 years ago, we observed that under this condition, pebble accretion can occur also in this post-main sequence disk, and they can allow the formation of planets in this disk. Interestingly, this process can support the formation of giant planets, and these giant planets can in principle be detected by gravitational wave emissions to the LISA mission. So this could represent one of the next frontier in exoplanetary science. But at the moment, this is only a curiosity that, however, highlights the importance of this connection between planet formation and the characteristics of the disk. But the disk doesn't affect only the physical characteristic of planets. It also affects the compositional dimension of planet formation. Specifically, and we continue with the surprises, circumstellar disks are illuminated by the central star and are characterized by radial temperature profile. So the farther you are from the star, the less luminosity you intercept, and the colder your disk will be at equilibrium. So if you move away from the star, at a certain point, the temperature of the disk will fall below the condensation temperature of water. This is what is called the water snow line, and is the transition between the red and the blue region in this infographic on the right. When we cross this region, instead of having only dust, we have a mixture of dust and ices. But this is not a characteristic only of water. Every element that is characterized by a condensation front or a snow line and condenses at a certain temperature in the disk. We see this in the solar system, recorded in the different abundance of volatile elements in the Earth, meteorites, comet, when we compare them to the sun. As you can see in the plot in the left, when we move from the Earth to the comets, we see that the abundance of oxygen, nitrogen, carbon and nitrogen increases, for example, with respect to meteorites. But also other elements are characterized by the same profile. And if we quantify this in terms of the condensed mass fraction, so how much material is in solids in a given region of the disk, we obtain this kind of profile. So in the innermost region, we'll have only rocks and metals, so the material that condense at higher temperature. Then we'll cross this line of water and we'll get water condensed. We'll have other elements that are more and more volatile than water, like ammonia or CO2 condensing, and so on. Increase the amounts, the fraction of heavy elements that are condensed in solid form, and they can contribute to the mass of pebbles that are accreted by the planets. In a disk of solar composition, the mass balance between rocks and ices is roughly half and half. So half your pebble, the mass in pebbles is represented by rocks, and the other half, up to the other half, is represented by ices. But this is not necessarily generally true, because compositional studies, surveys of circumstellar disks show us that stars of different metallicity are characterized by different abundance of volatile elements. And this is shown in these plots as a three-dimensional correlation between the elemental abundance ratio of nitrogen, oxygen, and carbon, or you can see it only as a dependence between metallicity and one of the elemental ratio. And you can see that there is a correlation. So the more metallic the star, the more the carbon over oxygen ratio is, the higher it is, meaning that carbon grows faster than oxygen with metallicity. So stars with more heavy elements are characterized in general, on average, by more carbon than oxygen with respect to the less metallic counterpart, like the sun, which is in this plot is the cross. Also in this case, however, as you can see, there is a large dispersion. So yes, there is an average correlation, but a star around a more metallic star can be characterized by a smaller Sierra ratio than a specific less metallic star, even if this trend in general grows. Un second. Ragazzi, scusate, potete abbassare un po' la voce? The same correlation you can see here for nitrogen. However, you can see that the slope is different, meaning that the abundance of nitrogen increased faster than that of carbon for a given metallicity. And you can spot this if you look at the color scale, as the red means higher carbon over nitrogen ratio, and green is a lower one. And you see we move from higher to lower for increasing metallicity, meaning that nitrogen goes faster than carbon. So when we have stars, even if they have the same mass, if they have different metallicity, they will have different abundance of volatile elements. And even if they have the same metallicity, they can be characterized by different abundance of ices, meaning that we don't always have the same composition of the star and therefore of the pebbles that move across the disk. And this is important also for the planet formation process, because we saw that, for example, planet formation, stars with different abundance of oxygen tend to favor different classes of planets. In this plot, you can see as the circle, these are stars hosting giant planets of mass above 30 Earth masses. You see it here, between 31,000 Earth masses, if you want, or between 0.1 and 3 Jupiter masses, while the squares are stars that are orbited by planets that are between 5 and 30 Earth masses, so a super Earth to a super Neptune. And as you can see, the square are systematically shifted at higher oxygen to silicon ratios. So generally planets, small giant planets tend to favor higher oxygen abundance, stars with higher oxygen abundance. Why so? Because oxygen is one of the most abundant elements and it makes up in a solar composition about half the total mass of solids, because between rocks, its contribution to rocks and ices. If we increase oxygen, we are increasing basically the abundance of heavy elements, even if we have the same metallicity, so the same abundance of iron, because in this case, we increase the ices. And if we run population synthesis models and we compare a disk of solar composition and a disk with the same composition as the sun, but higher oxygen, we see that we get more planets, and this is the same effect as increasing the metallicity, but we also shift the abundance of small planets with respect to that of high planets when you compare it to the solar disk. So instead of 1/4, 3/4, we get 1/3, 2/3. So composition also has the effect of changing the efficiency of pebble accretion and the kind of planet that we form. But this is only the most simple description of the effects of composition, and it is also the simplest description of chemistry and in circumstellar disk, which is the picture of the snow line that you see represented here. Other disks around other stars can be characterized by different astrochemical structure, even if they have the same composition. For example, we can have irradiation from the surrounding cluster. If a star is born in a cluster or near an B association, so you receive a flux of ionizing radiation and the position of energy, these can change the structure of the disk. You can see, for example, that adopting the same initial composition, we end up having molecules that were not present, like O2, that is not present in under low irradiation, and the snow line become more erratic. Or we can have stars that emit flares, and these flares warm up the whole disk. And these cause the molecules to reset to the elemental abundance and then restart their chemistry and forming molecules under different pressure temperature conditions than the ones they had in the native molecular class. And it can change once again the structure of the disk. And we can combine flares and ionization to get even more complex circumstellar disk astrochemical structure. Again, when we see circumstellar disk, when we see exoplanets, we don't know what was the chemical structure of the disk. So it is difficult to map this. We need to be able to connect the signature of planet formation to those of the disk environment. And for some reason, the presentation really liked to boycott me. So one idea on how to connect the composition to planets to that of disk was proposed almost 15 years ago, when it was observed that the elemental ratio in disk will change across the different compositional regions of the disk marked by the different snow lines. This was studied most for the two most abundant elements after hydrogen and helium, so carbon and oxygen, with carbon being slightly more volatile than oxygen, meaning that carbon remains in the gas phase longer, oxygen goes into the solid phase, so the gas phase will become enriched in carbon and get a higher C overall ratio the more we move to colder region, while instead we will have a substellar abundance C overall ratio for solids until we reach the region where all the carbon and oxygen are condensed. And the basic idea was, okay, if we can measure the C overall ratio of a planet, we can map this into where the planet formed. The intuition was brilliant, and the basic method is what basically we are pursuing even today. However, the picture is not as simple. First of all, because planet formation is a local process, in the sense that the planets form in a specific region of the disk only up to roughly 1 Earth mass. These are planets that we, at the moment, cannot see around other stars, especially if they are far away. After the planets grows beyond 1 Earth mass, it starts migrating in the disk. So while it grows, it also migrates closer to the star. And this means that it crosses different regions. So the C overall ratio of these planets will be a mix of the contribution of different compositional regions. And this introduces degeneracy in the composition. The other problem is that nothing. In disk, we don't only have dust and pebbles, which I remind you, they are basically the same thing. They are mostly differentiated by the sizes. So from millimeter above, they are generally identified as pebbles, and below they are generally identified as dust. But we also have planetesimal. And we know that there are planetesimal in protoplanetary disk, not only because of the record of from meteorites in the solar system that tells us that planetary bodies the size of present-day asteroids and comets or larger were already present around the young sun when the solar nebula was still existing, but we have the indication that they exist also from protoplanetary disk around other stars. And we get this from the fact that disks around a certain age, around 2 to 3 million years, show higher abundances of dust than younger disks. And this rays of dust is suggested to be due to the destruction of planetesimal due to the collision and the conversion of planetesimal into dust. Other evidences come from lines of evidence come from specific circumstellar disks where we see that there are regions where there is supposed to be little to no dust, and instead, as in the specific disk HD 163296, these regions show the highest abundance of dust. And again, this has been shown to be due to the collisional evolution of planetesimal that inject new dust into the disk. And what happens when in disk we have also planetesimals? What happens is that we need to resolve the interaction of the growing planets during the growth and migration also with the planetesimal disk to simulate how this interaction translates into the composition, affects the composition of the planet. Here you can see 4 snapshots of the formation process of a planet embedded in a planetesimal disk while it is growing and migrating. And as you can see, planetesimal get their eccentricity increased closer to the planets, and then when the planets start to become a giant, also farther away. Higher eccentricity means the orbits are elongated like those of comets and can cross wide region of the disk. Part of these exocomets will impact on the planet itself and will affect its composition. The major problem with this process is that if we compute how much mass this planet is accreting for the different compositional region of the disk that I map with the different color, you see that the contribution of the different region is not the same. Meaning that when what we get into a planet is a mixture of material, different amounts of material accreted from different regions. So there is not such a one-to-one correlation as it was originally suggested 15 years ago between a specific region of the disk and the composition of the planet. A solution to this problem is obtained by mapping the composition of the planets across multiple elements and computing multiple elemental ratio. Why? Because once again, there is the last problem with that simplified picture of connecting the C over ratio, so carbon to oxygen abundance ratio of disk to that of planets, is that when we use the most updated information on the abundance of carbon and oxygen in solids, the one, for example, for comets that I was showing you before, we discover that the C over ratio of planets is limitedly sensitive to the formation region and migration history of the planets. So if planets accrete, independent of whether planets accrete only gas from the disk or gas and planetesimals, which is the purple curve and the green curve, in this plot, you see that the curves are basically flat. So we don't, it's not very easy to identify what is the formation region of the migration history of the planet, because all the planets end up having very similar to within 10 to 20% C over ratios. The situation, however, gets much better if we use an element with a different volatility, like nitrogen, where we get, once again, these monotonic trends that deviate by the stellar composition as it was proposed originally for the carbon over oxygen ratio. However, one thing that you might notice if you look at the y-axis of this plot is that the elemental ratio of different elements have very different values. Like the C over ratio goes between 0.5 and 1 roughly. The N over O ratio goes between 0.1 and more than 1, so twice as large a range of variability, if not more. And the C over N ratio instead goes over more than a decade, or at least a decade of value. So how can we compare these elemental ratios? Again, the stars comes in our help, because if we normalize the abundances on the planets to those of the stars, so we need to characterize not only the planets but the star and do the extra effort, this extra effort pays off because we can bring all the elemental ratio on the same scale. And one thing that you can notice is that if we have planets that accrete only gas from the disk, or planets that accrete gas and solids from the same disk, you see that the color pattern is inverted. This means that the elements are enriched in opposite way. For example, if the planets accrete only gas, N over O is going to be greater than C over O, that is going to be greater than C over N. So even if we cannot precisely measure the value, we just need to know the order, that the elemental ratio are in these orders, to know these planets mainly formed by accreting gas from the disk. If the order is the opposite one, the planets formed by accreting gas and planetesimals. So if we can, the connection between the planets and the star can help us get this insight, notwithstanding the challenges in precisely pinpointing the elemental abundance inside a planet. We can extend this process. For example, the plot on the left that you can see is a multidimensional view of what I was showing you before, where you can see mapped in two elemental ratios, and you can see the different accretion history, blue and green in this plot, or different disk astrochemical structure, the rosette, so we saw the stars emitting flares and altering deeply the astrochemical structure of the disk, or the disks that are preserved for in terms of composition for the native molecular cloud, they map into different regions of the parameter space. So if you can measure multiple elemental ratio, at least the three elements, carbon, volatile element, carbon, oxygen, and nitrogen, we can measure the same elements in the stars, and we can use this normalized elemental ratio. We can get information on the nature of the disk in which the planet was formed and the main source of the heavy elements of the planet. If you noticed in the previous plot, I was also showing another element, sulfur. There was an additional curve. Why is sulfur important? Because sulfur becomes another refractory element, or a tracer of the accretion of the refractory component, the rocks, through planetesimal accretion. And the signature of the accretion of solids by giant planets, when there is the accretion of gas, is extremely different for pebble accretion and planetesimal accretion. Specifically, pebble accretion favors more volatile elements. So the more volatile you are, the more you accrete efficiently. So between carbon and sulfur, carbon is more volatile and is accreted more efficiently. So C over S is higher, as you can see here. Planetesimal accretion favors the accretion of more refractory elements. So sulfur is accreted more efficiently than carbon, and C over S decreases with larger accretion and metallicities. So the pattern, if we can measure carbon over sulfur, or the abundance of sulfur and carbon and another element in stars and planets, we can also discriminate if the accretion of solids was due to pebbles or planetesimals. My final point on the importance of connecting the stars to the planets is linked to an effect that is surprisingly very well studied for stars, especially brown dwarfs, where it is studied because it alters the composition of the atmosphere. And this effect is the sequestration of oxygen by refractory elements, specifically silicon, magnesium, and iron. Oxide of silicon, magnesium, and iron are the main component of the rocks or the dust in circumstellar disk. So they remove oxygen from the gas to form the dust and leave less oxygen to form volatile species like water or carbon monoxide. But the reason why people were focusing on the carbon over oxygen ratio is that the molecules of carbon and oxygen, specifically water, CO, and CH4, are very easy to detect and have very strong signature. So they are the ones that are generally used to measure the C over ratio of planets. But if we only measure water for tracing and CO to trace oxygen, in planets that are below roughly 1000 Kelvin, we are missing a part of the oxygen. Meaning that when we measure C over O, we underestimated the oxygen and we overestimated the C over O ratio, which can suggest completely different formation histories for the planet. So if we know the abundance of elements in the star, we can measure at least one element that traces rocks for the planet, like for example sulfur. Then we can scale that specific elements to the abundance of silicon, magnesium, and iron, compute how much oxygen they sequester, and correct the C over O ratio in order to get a proper information from the composition of the planets and information history, plus an indication of the presence of the accretion of planetesimal and their role in affecting the composition. So this concludes our bumpy journey across the genetic link between star, protoplanetary disk, and planets. And I'm happy to take questions to clarify any passage or satisfy any curiosity you might have. And thank you for your patience with the technical inconveniences.
Was using genetic a specific choice to draw an analogy to biological life?
Yes. Yes, the intention was exactly this, because exactly when we study biology and biological system, where we don't look only one specific, we don't look only at a specific, for example, microbe or life form, but we need to look also at the relation with the environment in which it lives and the world, and get a whole systemic approach in studying them. The same is true for planet formation. Studying planet formation without taking into account the environment of the disk doesn't provide a complete view of how the process can evolve and how it can shape the outcomes. And taking into account the disk without the connection with the stars also doesn't give us a proper answer. Basically, there is no one size fit all when it comes to planet formation, and we need to take into account um, the connection between the physical processes and the environment in which they take place. So I see that there is also Maria Rosa that has a question, and I'm wonder.
Yes. Thank you, Diego, very much for the presentation. It's very nice, very clear. I have one question for you. According to your models, what would you say is the smallest metallicity that can be or theoretically can form planets, massive planets and small planets?
So in terms of massive planet, there is actually a recent paper by the group of Bertrand Biche, and they were suggesting that the limit in metallicity is minus 0.6 in terms only of iron abundance, however. As I was saying, however, depending on the abundance of volatile elements, especially oxygen, and oxygen is higher proportionately for lower metallicity star, this can also compensate. So it will vary. Probably there is more leeway than going down below 0.6 in metallicity, but that should be a reference limit. So when you go down 3 times, 1/3 of the metallicity of the sun is a sort of limit for giant planet formation. For smaller planets, it depends how you classify smaller. If it is Earth-sized planets, as we were seeing, it's reasonably easy to form them around stars that are not too different from the sun. If we go to smaller stars or smaller disks, we can form still very easily planets of the size of Mars. But these are objects that are very difficult to observe.
Hello?
Yeah, that's true. Yes, and also the
אני
second
באמצע
question.
ההרצאה, אני עכשיו צריך לענות. שנייה, אני אתקשר.
I don't know if I can continue or.
There was a question by
Okay.
Amory Wendell.
Yes, hello.
Hello.
This is Amri Vandel. Yeah, again, congratulations on the talk. I'm trying to work on something that is related to giant planets on a general scheme. And of course, our solar system is not the best example to generality, but could you conclude from your work on parameter space, actually, if there would be something similar to the frost line, and what would be its dependence on the metallicity of the protoplanetary nebula?
So, generally speaking, the first line or the water snow line, because generally when we talk without specifying the molecule, we are referring to that of the water, is going to be present in all protoplanetary disks that are cold enough in certain regions. And this can happen both in space and in time, because also the disk will cool down over time. So at any given, at a given point and place and time in the disk, there's going to be this first line. And this is going to be a region where there is an enhancement in the abundance of solids. So it is speculated it is a favorite region for planet formation. How big this bump, this enhancement in the fraction of solids will be, depends on the metallicity. As I was showing you, for higher metallicity stars, the abundance of oxygen grows less than other volatile elements and less than the abundance of, for example, iron and rock species. So we might have that these stars are less ice rich, and the snow line has a smaller effect, like we can have the opposite for lower metallicity stars. So
Yeah.
it's going to
Yeah.
be something that depends a lot on the stars that you are studying.
Yeah, but what I was more at, if we look at the end product, where we expect to find the giant planets at the end of the process, and what would be the dependence of this water frost line at the end of the process of planet formation as a dependence on the metallicity?
Okay. That's a good question, because one of the problems is that we don't know the occurrence rate of planets at larger distance, if not for very massive ones. So at the moment, there is still a lot of bias, and we don't know, for example, if Jupiter is a canonical planet, a very abundant planet, or a very rare one. Observationally, at the moment, we don't see a lot. And observationally, it would seem that hot Jupiter are more abundant, but that's an observational bias. So
yeah, of course, but I
the
meant
higher the
according to your
metallicity,
simulations.
according to our simulation, higher metallicities or higher abundance of ices will favor the formation of planets at larger distances, because they will make giant planets formation, core accretion, more effective, because there is more mass to accrete. So the core grows faster and it migrates less during the migration. If you have lower metallicity, the planets have more time to migrate because it's going slower, and this will favor planets that are closer into the star.
Yeah. Okay. Fair enough. Thank you.